The solutions and explanations for the solutions to the projectile motion homework problem. If you notice, all the ones that were assigned, so that's from physics classroom, that problem set on projectiles and vectors, 21, 22, 23, 24, 26, all of those are for horizontally launched projectiles. 28 is the only one that is an angle launched projectile. The optional ones, 27 is horizontally launched, 29 is an angle launched one. So most of these are horizontally launched because first year physics, that's what we deal with most of the time. Really the big difference between horizontally launched and vertically launched, or pardon me, angle launched projectiles deals with splitting up the initial velocity into horizontal and vertical components for the angle launched projectiles. So with this, we have someone skipping a stone, I believe. Let's see here, because they always have good names in physics classroom. Dylan and Sophia. Oh well. And I think Dylan is skipping a stone, leaves his hand horizontally at 26 meters per second, 0.45 meters above the water, and you're asked to find how far it moves horizontally before it hits the water, as well as the time it takes to hit the water. So the time to fall, we need to think vertically. So we're going to use this version of a formula we've seen many times before. There is no initial velocity vertically. This is horizontal, so it is not appropriate to put it in this vertical equation. So that allows us to use a simpler version of that equation. Delta y equals 1 half at squared, and that time is 0.30 seconds. For part B, if you're asked to figure out the horizontal distance before it hits the ground, there we only have one question or one mathematical problem formula for horizontal motion, and I've rearranged it to solve for this. This is the average velocity formula, so horizontal velocity times time gives us that distance. PC22, I know he's been waiting for this. 16-year-old Matthew Watros runs off the high dive at a speed of 4.6 meters per second. Once again, we're going to use this version to figure out the time it takes to fall. And again, rearrange, take the square root to find time. A lot of times if people get this incorrect, they forget to take the square root. The horizontal distance, delta x over delta t. So rearrange that, vh times t, and that would be 3.17 meters. That's almost 10 feet, so he was going pretty fast. For part C, to find the speed entering the water, this does require a vector solution. So you might be able to think about just doing Vf equals Vi plus A times T, and realizing that if this is a vertical equation, there is no initial vertical velocity, and that would get you an answer, but that's only the vertical velocity. If we want the overall speed, and we've got a horizontal speed that's consistent and a vertical speed that is increasing and finishes up at that amount, this total speed you enter the water is the Pythagorean theorem resultant of both those. So that's around 8.2 meters per second. So that was a little tricky. PC23, again, something's being thrown off the school, trying to hit my car. I guess an angry student trying to chunk a pumpkin. So once again, trying to find the time to fall, use this and rearrange. Now to find the horizontal velocity. This time we know the distance and we know the time it took to fall because we just figured that out, and that gives us the horizontal speed at which something was thrown. Oftentimes what we're asked to do is, given the horizontal speed, asked to find the distance. Here we were given the distance, asked to find the horizontal speed. Okay, problem 24. This is the divers above the La Cabrera cliffs, I believe, in Mexico. So we're going to find the time falling at first like we normally do. Notice it's a lot more here because this is a lot higher. To find the horizontal speed at which they've got to be running to land out this far, we simply take that distance, divide by the time we just figured out, and that gets us that speed. That is a fast speed. Problem 26 is the last horizontally launched one. It was, I believe, something going on in my room, maybe. Actually, no, that's the Choo Choo restaurant. Yeah. I kind of always wanted to go there, but anyhow. We've got a French fly leaving the horizontally at 1.25 meters per second. The floor is a little over a meter below. First, we just find the falling time. You see a pattern. I see a pattern. And then you need to find uh, the distance it travels by multiplying that time times the horizontal speed, which was given to you. So that's about 0.29 meters. To find the vertical speed just before it lands, we use A times T, and the vertical speed increases by 9.8 meters per second every second, and it was accelerating for that much time. So we get a final vertical speed of 2.26 meters per second. So horizontal speed, vertical speed, and then the result was around 2.5 meters per second. So it's going at an angle when it hits the ground. PC28, that is our only one where we have an angle launch projectile. First part, figure out the horizontal and vertical components. So if I know we're launched at 8.06 meters here, that is the vertical velocity and that is the horizontal velocity. Horizontal velocity does not change throughout the course of a projectile's flight. Vertical velocity does change, and in particular, it changes at 9.8 meters per second every second. So I need to use opposite over hypotenuse, which is a sine function, to get the vertical velocity. I need adjacent over hypotenuse to get the initial horizontal velocity. That's a cosine function. So I end up getting vertical velocity is about 4.0 meter per second. Horizontal velocity is around 7 meters, 0.0 meter per second. Next, it's asking you to find the time to the midpoint. And I mentioned in class that I like thinking about projectiles in the first half or the second half of the problem, either way. So the vertical velocity starts at 4.03 meters per second. At the maximum height, though, the vertical velocity is 0 meters per second. And since we know the consistent rate at which vertical velocity changes of 9.8 meters per second every second, we can use this version of a formula we've already used for linear motion and figure out the time interval change in vertical velocity over acceleration. That's about 0.41 seconds to reach the midpoint, and then the total time up and down would be double that, 0.82 seconds. Part D, again, this is similar to what we've already found out once we know in the earlier horizontal problems. If we know the total time that this thing is in the air, we just multiply it by the horizontal velocity. Again, not the velocity here at the diagonal and not the vertical velocity, but the horizontal velocity will give us our horizontal distance. For part E, it's asking about the maximum height here. So this happens at the midpoint. You could think about this as rising and think about the initial vertical velocity up and acceleration down. That makes for a more complicated formula. Or we could use our old friend here and figure out the distance that it's falling during the second half of the trip. So the second half of the trip, it's falling 0.41 seconds, and gravity is accelerating at 9.8 meters per second every second. And so that gets us our change in vertical displacement of 0.82 meters, and so that would be the maximum height. For the bonus problems, those are listed here, very similar. Here, the only thing that's a little bit different for PC27 is you're given this distance, you're given the initial velocity. We're going to use that to find the time that it's in the air, and then work our way backward to find the height. So using horizontal information, since we've got two pieces of horizontal information, displacement and velocity, and then we rearrange that to solve for the time, and then we use time and gravity's acceleration to solve for the height at which something was shot off the edge. For 29, this is it says, what is it, the famous Chinese ski jumper Li Ping Far. Well, that's just another one of their puns, I suppose. Just like how PC27 was Aaron again and Bud Durfinger. So Aaron for error and Bud for Butterfinger, meaning slipped up. Anyhow, Li Ping Far launches from 34.9 meters per second at a 35-degree angle from the horizontal. So I drew a little picture over here. And even though it didn't ask for that, I found the vertical and horizontal components first. Vertical component was 20 meters per second, horizontal component 28.6 meters per second. So the time of flight is equal to the time up plus the time down. There's a couple ways you could have done that. Change in vertical velocity divided by acceleration gives us time. You could either do for half the trip and then double it, Or you could recognize that you're going up at 20 and down at 20. Those are going to have different signs. So our total change in velocity is actually 40 meters per second. And that happens at 9.8 meters per second every second, giving me a total flight time of 4.08 seconds. This is something similar to what we've done before, finds the horizontal displacement, and this will be how we find our maximum height. So you use half the total time and 1/2 AT squared to find that maximum height. That's very similar to what we did up here, or pardon me, up here. So notice it's half the total time. Anyhow, hope this helps, and hope you're successful on these.